Okay, hello everyone. Welcome to exploration into convolutions, activation, and pooling for the convoluted neural networks. Today we will be exploring the hyperparameters of the model using the basic Python libraries. So I have uploaded few images into this Kaggle notebook, and we'll use some of this to see the impact of various hyperparameters, as well as try to visualize some of them. So firstly, of course, our goal is will be to implement the convolution process. So taking the input, running the filter through that, and generating the output. And the first thing we need to do is to be able to show the image or convert the array into the image so that we could see it, and we'll do it in grayscale. This is the small code I have borrowed from John. Thank you for that, John. And I changed it slightly to be able to accept any type of array. And now, for instance, if we are given an array 8 by 6 and try to visualize it, so running this code, we can see essentially each number is represented by different colors. So similarly, we could create a random array and visualize it as well. But for our today's purpose, the sample 8 by 6 array would be sufficient. So where we start, we will first create a couple of filters. One is so-called vertical filter, where you can see the numbers 1, then 0, and -1 aligned vertically. So it can be visualized like that picture image. Horizontal filter, the other way around, so 1s, 0s, and -1s aligned horizontally. So that's the image of that filter. And the convolution process will take the array, so our original 8 by 6 array, and run the filter through that array. Now I have put these two lines here to determine the shape of the number of rows and number of columns in the array, so that we could accept both square and rectangular filters in our convolution function. And essentially, as a result of the convolution, we expect to have the new shape, which is going to be equal to the original shape size minus the filter shape size plus 1. And essentially, the process takes the small 3 by 3, for instance, arrays from the large array and multiplies each values by the values of the filter and sums them up and creates a new array based on the results. So let's run this code to see the result. So if, for instance, I take the vertical filter, take it through the original 8 by 6 array. So as you see, the result comes out to be 6 by 4 array. So we lost 2 rows and 2 columns in the process. And here's the visual representation of it. Now, in general, we can have the convolution process going through each cell in the original array, or every second, or every other cell. In this case, we call it stride 2 convolution. And as you can see in this function, so the only thing that changes is that now the shape of the resulting array will be twice less than original, not original, but changed due to the filter. But sometimes that could end up with the decimal number, so I had to put the rounding and change it into integer. So this stride 2 convolution will now reduce the image size twice. So we have now, instead of 6 by 4 array, for instance, we had the result of convolution previously. Now it results into 3 by 2. So that's the new array. Of course, this function could be further generalized by making this stride as an input. So I set it to default 1, but technically it could be any number of stride and running this new function over the same original array. So for instance, if I run it without any argument, stride argument, it will result in 6x4 array. If the argument is 2, so stride 2, so result is 3x2, and we can even do the stride 3, well, the result will be 2x2 array. Right, so that's the convolution process. Now, as you have noticed, in all of the previous cases, we end up with the smaller size image as a result of convolution. And of course, in the process, some of the information which is at the edges of the image might be lost. So that's why there is a process called padding that could be implemented on the original array to try to retain some of the information as well as the size of the original image. So, for instance, this pad function essentially creates so adds zeros around the original array. So here's the example. So our original array was 8x6, and we have the zeros around it. And of course, sometimes, and the result of it, of course, will be that if we now run the filter through the padded array, the resulting image will have the same dimensions as the original, right? 8x6 here, as you can see. Now, of course, the same as with the convolution with different strides, we can have several columns of padding and rows. So in this particular case, this function essentially sets the argument of how many paddings we need. So first, if I put 2, so have 2 zeros around the original array, or 3, here we are, depending on how much additional padding we need. Now, in most cases, though, our key goal for padding is to retain the original size of the image, and that's why we normally have the same padding, where the padding should be based on the size of the filter. So if, for instance, in this function, so I pass through the array and the filter, so the function will determine how much padding needed for the original array. And for instance, here, for instance, if I'm passing through the vertical filter, which is 3x3, we have 2 extra rows and 2 extra columns of zeros added. If, for instance, we had a 4x4 filter, this one is an example, and I pass through this 4x4 filter, as you can see, we added 2 columns of zeros and 1 column of zeros at the in the front, 2 columns of zeros and the 1 column of zero at the end, and the same 2 rows of zeros in the front and 1 row of zero at the back. And with the 5x5 filter, of course, process will be similar. So we are adding now 4 columns of zeros and 4 rows of zeros. So that's basically padding and convolution process. Now, normally, after the convolution process, we have activation function, and most commonly used one is ReLU, which is essentially finding the basically changing all the negative values into positive ones. There is a very short function here, as you can see, just returning the maximum of 0 or the original value. So if I take my convoluted array from above and pass it through this activation function, we can notice that something different happened. So let's actually pass that through here. And we can see that all the negative values became positive. So that's the activated now array. Now, after activation function, we normally have pooling functions. So pooling functions have 2 goals. One is to reduce the spatial dimension of the input, or so-called downsampling. And sometimes it allows to create invariance to local translation, meaning that slight changes in the shapes of the picture rotation will be still considered the same or will be recognized essentially. And for that, we use the max pool link function. So what max pool does is essentially takes the so we pass through the dimension of this max pool. So it takes the 2x2 shape from the array and essentially returns the maximum value instead. So as a result, of course, the size of the array will be reduced twice, right, horizontally and vertically. And let's see how it works. So say our activated array, and if I take it through the max pool function, so you can notice that if I take the first 2x2, all zeros, so that returns 0. The second 2x2 returns 0 again. The third one, 2x2, has 6, 3, 8, 0 in it, so it returns 8, and etc. So pretty straightforward, I hope. And the alternative for the max pooling is so-called average pooling. So the benefit of average pooling, if we is that it's useful when we actually want to retain the position of the objects in the picture, if it's important, and essentially it helps us for contrast learning, essentially between images. So the process, however, is pretty similar. So rather than taking the max, we have the average of the values within each dimension we have chosen. So, for instance, going through the same, taking through the weighted array through the same, through the average pooling gives us the array where now the values, as you can see, that became decimals. So that means that we are finding the averages of the values. And so that's the impact of the average pooling. Now, to see the actual impact of all of these hyperparameters, let's see one example. So as you can see, I downloaded the picture of a dog, and now I have changed it afterwards into the array, number array. Right, as you see, this image contains 423 rows and 433 columns, and which, if we, for instance, convolute using the horizontal filter, right? So this is the result. As you can see, we end up with more horizontal features, right, reflected in the image, right? All the features are silent. If we take the vertical filter, so take the vertical filter through the array, so now the more vertical features are reflected. Now, to see it better, I copied these two pictures into the Word file here. As you see, the vertical filter focuses on vertical features, while horizontal filter focuses on horizontal features. Another thing we could check what if we change the filter size from 3x3 to 5x5, right? We created that vertical filter 5x5 earlier. So in this case, you can see the features slightly different from the 3x3. You need to see the difference. So here's the side-by-side comparison, 3x3 filter, vertical filter, and 5x5. As you see with 5x5, the features are a little bit more pronounced, but I think also we have a little bit more noise than with the vertical filter. So as far as I understand, most of the processors recommend actually the smaller filter sizes rather than big. So what else we could do? So let's actually go through the whole process, like one layer. So starting with the array, padding it with the same padding to make sure that we don't lose any information on the edges. Then we'll take it through the convolution process using the vertical filter, activation, function and the max pooling. And when we do so, this is the result of a vertical filter. As you see, the very fine lines, vertical lines remain, while the other features of the dog virtually impossible to see. If we do the same with the horizontal filter, then we have the more only the horizontal features, or close to horizontal features remaining, while the vertical and other features disappear. So again, looking into this side by side is the difference. I think that's more clearly can be seen here. So what is important is that everything else besides these specific features we're looking into are technically lost in the process. Now, what if we do it the same, but with the average pooling? So these two set of code do the same process as before, but with average pooling. Again, to see the result side by side. So here's the left side vertical average pooling, right side the horizontal. Now it's better to compare this to the previous max pooling, and technically you can see that a little bit maybe more details with the average pooling than the max pooling, which is of course logical, and max pooling tries to get the main features, so most pronounced features in each part. So that's the max pooling versus average pooling. Now, final thing I wanted to look into is, okay, so we have stride within the convolution process. I have to remember this convolution with the argument 2 means that I can use the stride of 2, but also we have the striding in the pooling process. So what if so our original, layers essentially using the stride 1 in convolution and stride 2 in pooling, which matches the dimension of the max pool. Now, what if we revert it? What if we have stride 2 during the convolution process and stride 1 into the in the max pooling process? So this is what we end up with the vertical filter. And this is the result of that process with vertical filter, and this one is with horizontal filter. You can probably already see that there is a difference from what we had previously. And again, to see this, here's another round of pictures side by side. So the top two, this is the striding 1 in the convolution process, and stride 2, polish the other way around. So stride 2 in the convolution process and stride 1 in the pooling process. The below is stride 1 in the convolution process and stride 2 in the pooling process. So as you can see, stride 1 in pooling process leaves a little bit more noise, right? More of features that are not specific to this filter, which of course means that the using the stride 1 in the convolution and stride 2 in pooling probably will result in better outcomes. Okay, so that was it for now, right? And I hope you enjoyed it, and it was informative as well. Thank you very much for your attention. Bye.